Greetings and salutations throughout all of space and time. We're going to look at finishing molecular reactions where we take two ionic compounds and we mix them together. And then, once we have it written cleanly, we're also going to talk about what's really happening in solution, what we call a net ionic equation. Alright, so let's take a fairly straightforward example. We have a clear, colorless solution of silver nitrate. It would just look like water if I had it here. And another solution that would also look a lot like water, clear, colorless solution of sodium carbonate. If I were to pour these two solutions together, they would create something that looked like milk. It would be cloudy, indicating that we have a precipitate, that we have a heterogeneous mixture, that we have something mixed in that liquid that's not a liquid, if you will. So we'd have solid particles in there. And eventually they would cluster and they'd fall down. And a solution leaving a clear colorless solution and a white solid layer in the bottom. So how would we represent that reaction? And then what's really going on with the ions themselves? Okay, so let's start with, we're given two reactants and we need to predict the products. I like to call this changing dance partners. You might notice silver is a metal, sodium is a metal. These are ionic compounds, and the first step before you do this is we have to figure out what our ions really are. So again, with my little cut the heads off, and see what's left behind. So this is Ag by itself, that's simple enough. It's in the transition metal, so I don't know what the charge is, but I can get it from the anion. We have NO3, and again there's two capital letters in front of that 3, so we keep the whole thing together. I have correctly memorized that the charge in NO3 is -1. And if we have 1 minus 1, to balance it out, we need a single positive 1. And again, you could do the charge balance equation, silver plus nitrate equals 0, plug in -1 and solve for silver. But this one's straightforward, so I think it's easy enough to identify that it's Ag plus and sodium minus. Over here, now we have this situation with the 2. We only have a single capital letter in front, so it's really 2 sodiums. Right now, we're going to ignore that 2 part, and we just want to look at sodium. That's in family 1, so +1 charge. 2 capital letters in front of this 3. It's polyatomic. Keep the whole thing together. CO3. And then we correctly memorize as 2 minus, so that we have 2 positives, so you could also balance it out that way. These are our ions. So we're going to swap dance partners. We're going to put the other cation with the other anion and put them back together. Now, sometimes when people are first learning this, they may write something like NO3Na. Remember, chemistry is a happy, positive place. We always start with the positively charged thing. And we do have to balance out the numbers that we have of each. And again, that's why I want to ignore this, because it's really not important for predicting the products. It is for balancing them when we're done, but for right now, I just want you to look at the 4 ions we identified. Ag plus, NO3 minus, Na plus, CO3 2 minus. Let's just start left to right. This is a +1. This is a -2, so I need 2 positives to balance out 2 negatives. So our first product, and I didn't do very good board management here. My first product is going to be Ag 2 CO3. Put a little line there, remind myself I got to balance it. I'll put a little parentheses there, remind me I have to apply solubility rules. Same thing over here. Now let's look at the other parent. -1, +1, that's 1 to 1. Put the positive first. Chemistry is a happy positive place. NaNO3, and we're doing pretty well. So let's apply solubility rules. That might be the easier of the two things. So silver is not in group 1. It's not a polyatomic. Carbonate, CO3, if I put H's in front, not a strong acid, and it's not the acetate exception I asked you to learn, so that's 2 no's, so we put a solid here. Na is in the first family. We look no further. We put AQ, and we're done with that part. So that's not too bad. All right. Now we have to balance. Take your biggest, most complicated thing and put a 1 in front. Now I have 2 silvers to balance that out. I need silver. They come in groups of 1, so 2 over 1 is 2. And do the same thing here. I have 1 carbon here. I have 1 carbon, 1 over 1. And then lastly, I have 2 sodiums. They come in groups of 1, so 2 over 1 is 2. And we've now done, if we were to write this cleanly, written something called the molecular reaction or equation, depending on your source. I like reaction better because that's what's really going on. And just to review concepts, we're going from aqueous, from a solution, to a mixture. We have a solid here, so this is known as the precipitate. And this whole reaction would be a precipitation reaction. So just reviewing some concepts and terms. Let's go a step further with this balancing. So hopefully this is the same thing we just got on the other page. So again, this is our precipitate, and we're going to start to, and again, this is not a good representation of what we have in solution. So we need to represent this better from a chemical standpoint. It's certainly balanced, it certainly gives us an idea, but we'd like to better represent the chemistry occurring. So just to make this as clear as possible, solids, liquids, gases, when we're doing these ionic equations, whether it's complete, net, or any version of ions, leave them together. A lot of times in class I'll say leave them to bleep together. And I do bleep, I don't actually use swear words, but leave them to bleep alone. Leave the solids alone, leave the liquids alone, leave the gases alone. I know we do enough of these, you get in the habit of blow everything up. Blow it up, break it up, break it up, break it up, break it up. Just caution. If you see a solid, liquid, gas, pause and go, hey, I need to leave this alone. Okay, so now that being said, well, this again is not a good representation. Your strong electrolytes are broken apart 100%. So we need to do that in these equations. We need to ask ourselves in every one of these instances, is this a strong electrolyte? Solids, liquids, and gases, the answer is no, and we're done. But for anything with an AQ, we need to ask ourselves, strong or not? I suppose strong or weak in this case. So Ag starts with the metal, it's got an AQ, boom, strong electrolyte. We're going to break that apart. Again, just cut the head off. Starts with the metal, AQ, we're going to break that apart. Solid, ooh, I got to leave that alone. Sodium starts with the metal, got an AQ, we're going to break it apart. Simple as that. So now we have to break it into all the pieces, and the balancing matters. So remember, when you have a 2 out front, that's 2 of everything that follows. Everything out there. Anything that starts with an AQ, ends with an AQ. So for example, I have 2 silvers, and we remember that we have a +1 charge there. It's actually handy when you're working these problems. You know, the first thing I did was identify my 4 ions. Keep that handy so you have that. That should never change. That should be consistent throughout all these processes. We have 2. This is what mistake a lot of people make. They forget the 2 on the back end. The 2 here is easy because it's right there, but don't forget it on the back end. We also have 2 nitrates. And again, just 1 cation, 1 anion. Cut the head off, everything else stays together. Sodium carbonate. Now we got to bring that 2 up front. Remember, only 1 capital letter, so the 2 comes up front. 2 sodiums. And then carbonate stays together. And you can see, even though I'm writing smaller, I'm still running out of board. So that's the left-hand side. Right-hand side, we're going to leave that together. And I'm going to have to go to another line here. 2 sodiums. And 2 nitrates. Just breaking all the pieces apart. The charges matter. Putting your states matter. Balancing matters. All these things. There's a lot of the things here are easy to do, and it's also really easy to make mistakes. So this really does take practice, attention to detail, that type of work. So this is something known as the complete ionic reaction. It shows all the ions in solution. Silver's acting independently beforehand, floating along. Happy little silver. Nitrates floating along, doing the same thing. Whee! Also happy. Sodium floating along, super happy. We got 2 sodium. And carbonate, boop, bloop, 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 a little bit bigger, so it blubs around. It doesn't boop, 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 boop around. But they're all floating around. On the right-hand side, silver and carbonate become alternating positive negatives in a structure that goes on as far as the eye can see. And then the sodiums are still bloop, 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 and the nitrates are still bloop, 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 along. So my question is, sodium beforehand is floating along as a happy little cation, and at the end, it's floating along as a happy little cation. Has it done anything? Is it part of the reaction? Has anything happened? Is there any chemical change? And the real answer is nothing's going on there. So really not important. How about NO3? Nitrate, we got 2 nitrates, -1 charge, aqueous at the beginning, 2 nitrates, -1, aqueous at the end, and everything's got to match. The number's got to match, charge has to matter, everything's got to be exactly the same. But if it is, we cross that out as well. Now what's left behind is really what's happening chemistry-wise. This is what we would call our net ionic reaction, which is going to be 2 silver cations plus CO3 2- goes to silver carbonate, solid. Now, sometimes I get these questions. Does it matter if I go silver and then carbonate, or carbonate and silver? Well, 2 plus 3 is the same thing as 3 plus 2. The chemistry's right. It's good. If you want to look like a chemist, and let's be honest, who wouldn't want to look like this? I mean, it's pretty awesome, right? You put the cation first and then the anion, because chemistry is, yeah, I know, it's a happy, positive place. So we have our silver carbonate. So if you are using an online homework system, something like that, they're usually a little more OCD and they want it the standard practice way, so they'll want cation and then anion. But, 2 plus 3 is the same thing as 3 plus 2. Totally fine. I grade my own test. You're good to go on that. So that is precipitation reaction, net ionic, and these things we crossed out that aren't doing anything. They're the same thing, and I know some fans aren't going to believe me, but when you go to a game, you don't actually affect the outcome of the game. If you are sitting with on one hand and your team scores a touchdown, that because you sat on the hand, it really didn't help them score a touchdown. You can not do that for the rest of the game and it'll be okay. Trust me, it'll be okay. You have no effect on the game when you're doing these things. Much like these ions have no effect on the reaction. So we call them spectators. They're there, they're cheering on, yay, precipitate silver, precipitate carbonate, you guys are doing awesome. But they're not actually participating. They're just, spectating, watching the game. So we call those spectator ions, ions that don't. So any of these ones you cross out, these are your spectators. Might as well color code spectator ions. So in this case, it'd be the nitrate and the sodium. All right, and you can stop here if you want. I'm going to do one more quick example just for practice if you want it and summarize what we did, but you get the gist. Oh, you're still with me. Awesome. Okay, summary. We're going to swap partners. Figure out what the partners are and swap them. We're going to balance our reaction. We're going to apply solubility rules. And then if we need to do net ionic, we're going to break all the strong electrolytes, and then we're going to cancel out our spectator ions, and we'll be left with the net ionic, and we can celebrate and pat ourselves on the back. So what does that look like? I'm glad you asked. You can either go backwards or forwards in time, and here we go with another example. So first steps first. Realize aluminum and potassium are metals, and we need to cut the heads off in such a way that we don't destroy our writing space. All right. So Al is by itself. It's in the 13th family, so that's always 3 plus. There's only one capital letter, so it's really 3 Cl minuses. Potassium, same thing, only one capital letter, so it's just potassium. That's in family 1. And then PO3. We keep that all together, and we have correctly memorized that it's 3 minus, or we get it from the potassium charge. Hopefully you memorized it. And now we swap our dance partners. Swap, and we will get, remember the positive goes first, so Al3 and 3, so that's easy enough. Al, PO3. And we're left with K and Cl. Remember, put the positive in front. We can balance this. This looks like my biggest thing. I'll put a 1 in front. I have 1 aluminum, 3 chlorides, 3 potassiums, 3 potassiums. That would be a balanced reaction. We do have to apply our solubility rules. Aluminum is not in family 1. PO3, not part of a strong acid. Haven't memorized that one, so that's a question mark. So that's going to be our precipitate. Then we have K and we have Cl. K is in the first family, go no further. That's aqueous. There's our completed molecular reaction. If we get rid of the little funny orange stripe. And it's our balanced molecular reaction. And I know I did this quickly, but I wanted to show you a second example without making this video go on forever. I did forget one thing. If you have a reaction that's aqueous plus aqueous, goes to aqueous plus aqueous. At the beginning we have a bunch of ions that act by themselves. And at the end, we still have ions acting by themselves. We cancel everything out if we're doing net ionic. So this would be a classic no reaction occurs. There's no reaction to write, nothing you would do, you would just write no reaction. If you're given, say, sodium chloride plus potassium bromide, where all 4 of those ions are always soluble, this would be no reaction, for example. Soluble, 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 you would see that occur. Okay. Back to the regularly scheduled program. The 4 things I just erased you should never do when you're doing your own homework. Keep those for handy reference, but since I've done a few of these in my lifetime, I think we'll manage. So we want to break these apart. Al3 plus aqueous plus 3Cl minus aqueous. So again, metal, aqueous. Metal, aqueous. Solid, leave it alone. Leave it alone. Don't touch it. Stop touching the solids. Just leave it alone. Metal and aqueous, break it apart. Okay. Same thing here. 3 comes out front. 3 potassium ions plus a phosphite goes to aluminum phosphite solid plus 3 potassiums, and I'm going to make it 3 chlorides. Anything that's exactly alike on both sides is a spectator. Al3 plus AQ, Al, there's other stuff that's different. 3Cl minus, 3Cl minus, that can go away. Bye-bye, it's like the dodo bird. 3K plus AQ, 3K plus AQ, that also is like the dinosaurs. And then we have PO3, 3 minus, and that's different than AlPO3. So what's left behind is our net ionic equation, and we are done with this video. Thank you for hanging in there to the end. I hope you get good with this, and think about this next time it's raining and you have your precipitates, so singing in the rain.